Okay, so this lecture will cover Article 250 on grounding and bonding. This will take a little bit of time, but we will try to see how far we get today. Um, Typically, it always draws a lot of questions and so on these type of topics. So let's look at 250.2 and look at some of the definitions in regards kind of what the part about this is there's a lot of things that are going to be defined a little bit different. We've used the words like grounding, grounded loosely, and so now we really have to make sure that when we're reading the stuff, we know the definition specifically for every little thing. So let's start with the bonding jumper. And the bonding jumper, this is on the supply side. This is actually the jumper that ties, in essence, this is the meter. So that's your meter that's outside your house. Typically, this stuff will be in one enclosure, so this picture doesn't really apply. But if we did have two separate enclosures, we have to make sure that we take and bond the actual conduit between the main breaker and the stuff that's coming from the utility. And the reason is that um, if anything gets induced into this conduit, we need to remove those electrons that are going to be being carried back and forth in the wires, but we have to bond this stuff to make sure that we have we're able to dissipate some of those electrons in addition to protect and have conductivity from the wires that are coming from this side to this side. So the one thing is the neutral here does act and tie the neutral coming in from the service through the conduits back in here, but there is no insurance that or assurance that the conduit is carrying any electrons that get induced into it, and that we have conductivity. So if any short circuits do occur, the short circuits, and I'll show you here in a second how this whole works. If we know how this you have to kind of know how this system works, that all electrons that get induced into our equipment ground want to go back to the source, which is the transformer, and any separately derived source, separately derived, which means a transformer is separately derived, right? So let's look at this next picture because it'll actually talk about, so we're talking about the bonding jumper on the supply side. And then we look in here, for example, we have a ground fault. We're still looking at the supply side, but this is what happens with the transformer. What happens is any short circuit that goes, or any ground fault, not short circuit, ground fault, ground that goes to ground, a hot touches the ground, will actually get carried, the electrons will get carried back to the source through the equipment ground, but also through that supply side bonding jumper right in here. Let me see if I can actually, so where I'm talking about is right here. That is what we're talking about. We'll take it back to the source, and that's what I was talking about. We have to ensure that the electrons have free flow back to the source, and the source, which is the transformer, will also have a bonding jumper going to the electrical source, the electrical system. So we, in the United States, we like to use grounded systems. Grounded systems is exactly what we're looking at here. This is a grounded system on what happens when a ground fault occurs, that we facilitate, and what happens is the electrons that are flowing, for example, up here through this wire will go to ground and have free flow of current back to the source, which means that you're going to have this loop created here, right? A loop allowing the electrons to free flow back to the source, allowing for the breaker to work. So what it does is that if we, during ground faults, if we allow the ground fault to have a free flow back to the source, we will have enough current to trip the breaker. And that's how our systems work, is that we want the breaker to trip under ground fault conditions. Other places don't ground their systems, and they don't want the breaker to trip, but it could create a dangerous situation where now the equipment is like a live circuit, and if you touch another wire, you will complete the circuit, and so now it can become extremely dangerous with the higher voltage. Okay, now what we do in ungrounded systems is we have ground fault detectors, and that's how we can avoid this. And so sometimes we will do ungrounded systems. Like, for example, that tomato processing plant, there was a pump that was so critical that we actually ended up doing ungrounded system for that pump, that motor, because if that went out, it would actually cause pressures that could explode a chamber that they had over there in the tomato processing plant. But what I had to do is install ground fault detectors, or a system to protect and shut the breaker off, or make an alarm. In this case, it was actually an alarm. If one of the wires had touched the ground, we didn't want to trip the breaker. We wanted to just let everybody know by a horn that we have a ground fault, and it would just turn on the blare this horn out, so everybody knew, oh, we've got a problem. And at that point, they can turn the motor off in sequence. And because that sequence was critical to make sure you don't have to build up a pressure in a chamber that could actually explode. So for critical systems, we may be doing ungrounded systems, but in your house, in your commercial type applications, in the United States, we actually use this as the way our systems work, is that the equipment ground, and these bonding jumpers have very specific applications in trying to get the getting any electrons that go to ground fault actually go back to the source eventually and facilitate the operation of the breaker. Okay, so that's first thing that you have to be aware of. Okay. And so now we're going to look at the bonding jumper here, supply side, but in this case is a generator. The idea is that the source, we have a dual sources here. We have this is actually a pretty typical installation for, a hospital, for many places that actually have a generator backup system. And, you don't want to, if you lose power from the main service, so let's say you're going to have the utility over here. This is the utility here. So this would be PG&E over here. And then you have a you have a generator here, and we have a transfer switch in the middle. Right now, the transfer switch is set to power up my building from the utility. See how the little switches down here, I can actually see the red wire, I can follow it back, and it's switched over from PG&E side. But if we did need to switch it over to the generator, the transfer switch just automatically just flips over to the other side and now routes the power from the generator down to the panel board, right? So that's how a generator, I know some of you, have not seen some of this stuff, but this is a very typical installation that we work on where we have transfer switches. And actually you may have worked on I know there's a lot of, especially up in the hills, there's always a lot of customers want to have a generator backup system. So this is typically what in essence, how they look. in the case of you know, a generator backup for a house. I think you're going to find that we're going to see probably some of this stuff be more and more common in the United States. You see more, especially what was it? Well, Y2K, the year 2000, everybody wanted generators. I did a lot of generator work for people on the weekends, and but anytime that we start losing power, like PG&E right now, you know how they're having to do those forced shutdowns in the summertime because of fires, right? We saw an uptick of people wanting generators. So you're going to see a lot more of this stuff out there in the field being in demand, especially as wildfires, you know, what's happened, especially now that PG admitted to causing the fire for the Paradise Fire up north. The amount of liability and stuff like that, it's too great. So they're all these utilities are going to be extra cautious because it has cost them, you know, billions of dollars in liability and all this stuff. Anyway, the point of it is this is going to be very typical. So get familiar with this. This picture gives you a pretty good layout of how things work, but the grounding is extremely important. And notice also that the generator has its own grounding electrode conductor. So that's another thing that you know, generators will also have to have another ground rod close by. Anyway, just something to think about. Okay, we'll talk more about that stuff. And then, so 240.4 is a very important section for me. I always end up reading this part because it kind of, I think it gives us insight as into why we ground and bond. And our systems are solidly grounded. What we're saying is that's what we're talking about. We're talking about we take a solid ground to our system, and that's this is typically our systems that we're dealing with out in the field. It's not the only ones, okay? Sometimes we do impedance, high impedance grounded systems, which are just have different applications, a little bit more advanced topic in regards to that. But you guys are always going to be coming across a solidly grounded system. And so let's look at some of the terminologies of why we do certain things. So A1, 250.4A1 is really the primary reason is electrical power systems are grounded connected to earth to limit the voltage induced by lightning, okay, comma, line surges or unintentional contact of higher voltage lines to lower voltage lines. And so that might be where a car crashes into the pole, and the pole has the high voltage lines, usually are the highest ones up on the pole. And then, by the way, they usually kind of work their way down in voltage. The lower ones will be the lower voltage. So typically your telephone wires will be the bottom row, you know, Comcast, all the low voltage type systems will be down below. And then you'll have the medium voltage or the voltage like 120, 240 feeding houses. And then you'll have your high voltage will be 12,000 volts or something like that, 4160 on the top, you know, of the pole. So, and so sometimes the higher voltage lines can actually contact the lower voltage power lines. And that's what they're saying in their unintentional contact with higher voltage lines. So all this is saying that if we ground our system properly and we have these unwanted electrons that just pop into our system, that we will actually have the electrons be able to flow to the earth through these systems of ground rods and whatever we're using to get into earth. We'll be able to use that to dissipate any of these unwanted electrons that don't belong to our system. And that's a really important point as in why we do what we do, okay? It's really about lightning, why we put the earth ground and why we tie that everything to earth ground. And this comes from Benjamin Franklin and, you know, in his initial studies of the kite, with the key was diverting lightning strikes, because lightning strikes were burning down buildings in the early 1700s, and he was trying to figure out a solution of, so he's not the father of electricity, he's really the father of the lightning rod. So, you know, one of his many accomplishments, of course, which, you know, his accomplishments are not just in electricity. He was, you know, he did a lot, you know, the Constitution politically, you know, bringing the first fire station to the United States, you know, tons of other things. Anyway, so Benjamin Franklin's call to fame was basically to divert the lightning to Earth. And then we continued that as we brought our electrical systems. We continued that same kind of thought in trying to redirect lightning. So lightning, especially back east, lightning is a real big issue. Or if you're up in the mountains, you know, lightning will hit, and when it hits hard. So, and then so system grounding helps reduce fires in buildings, as well as voltage stress on electrical insulation. So it means that, you know, ensuring longer installation life for motors, transformers, and all that stuff. So if we were able to stabilize the voltage, you know, and if we are able to get rid of these unwanted stresses on the electrical system, then we're able to, you know, stabilize the voltage on the electrical system. So that's kind of the idea behind that, why we ground things and so on. We can use this as a pathway to get rid of all these unwanted electrons. For example, if we tie it into the system, the electrons that are parts for, let's say in this case, you know, lightning were to hit our wires or get into the building, it's going to dissipate through the main bonding jumper right in here, and then it will eventually go to Earth through the system, and so that's how that works. Okay. Oh, another thing is kind of important to make a point, and I did, because I had somebody, when I took one of these classes years ago, somebody said, well, you don't want to bend the wire because literally the lightning bolt will shoot out of the wire and it will bounce inside a room. Well, I was like, really? That doesn't sound right. So I did some research and actually found out that is true. That is true. If you bend the wires too much, you know, if you get a sharp bend, as electricity is flowing down that wire, you know, it's got all this back pressure behind it. Literally, the electrons will flow through the air, so it'll actually go through the insulation, flow out of the wire into the air, and literally bounce off the walls until it finds a way to get back to Earth. So there have actually been many cases of like, you could actually literally see all the burnt marks in the room where the lightning bolt actually was trying to move its way around, trying to find Earth. Anyway, so the point of it is we don't bend the wires excessively because, you know, so you don't want to make sharp bends on this stuff. You want to make curved bends, right? And the other thing is, because, you know, we try to minimize the length because, again, the longer the wire, the more resistance, yeah, like a corona charge, a discharge, yeah. So that would kind of like where it actually gets out of the wire and actually has an effect to go into the air, right? I think that's what you're talking about, Jonathan, right? Are you there? Yes, yeah. Yeah, it's the corona, kind of like corona effect, exactly. And so if you've taken like any like physics classes, and some of the stuff may make sense of why we do certain things. Unfortunately, they don't tell you the practical aspect of it, you know, kind of like, you know, how does this apply to our wires and so on. But literally, that's why we do the things that we do because physically electricity behaves certain ways, and we need to make sure that we control those pathways. So length is another important point, because the longer the length, the more resistance, the more, so you remember that rule that current tries, or electrons try to find the path of least resistance, right, back to the source. And so that could mean that an alternate pathway, which might be an unsafe pathway, may be the choice of the electron, right, to take that unwanted pathway. So our whole thing is to create pathways for electrons, and they're controlled pathways. So we're always trying to control the path that the electrons, whether during short circuit, ground fault, or overload, we're trying to control those pathways for electrons to flow. So that's what the grounding why it's so important, because we're creating a system that's not being used all the time, but it's being used only during the worst case scenarios, and that's why grounding, we put as much emphasis in grounding and a lot of other stuff. Grounding is very critical, that we don't, we don't screw it up, because then a whole building can burn down, people can die and stuff like that. So in almost all cases, system grounding is performed, not preformed, by the electric utility, since it's their system that provides the power to the premise. And that's true, but we also in our transformers, we do the same thing. We created a separate system inside the building, and so it's important that we actually understand this. So at least I do a lot of it, and commercial and industrial type applications. So again, any electrical metal parts of an electrical equipment must be grounded to reduce arcing within the building or structures from induced voltage, such as indirect lining. So we have to make sure we ground everything properly. So if something does get into those conduits. Induced can also be within our own wires. The electrons flowing through a wire can induce into the metal objects, right, to the ferrous material, and basically have electrons and excite the electrons to move in the conduit. That's why our conduits have to be properly grounded, so we discharge any of those unwanted movement of electrons within. And if we don't do that, we create chokes where the electrons will not be able to flow, because as you remember, it's basically a big inductor. Our conduits act as a big inductor. They also act partially as a capacitor because of the insulation between the wires and the and we have two dielectric, we have two conductive objects, which is the conduit and my copper wire, and then we put a dielectric in between there, which is the insulation. And so there is some form of, it's not that big of a deal. It's not something that we get concerned with, but what happens is, because of capacitive and inductive effects, that we actually have to be very careful to ground everything so it doesn't act as an inductor or as a capacitor, right? So, okay. So this is, if we fail to ground things, metal parts can result in high voltage from an indirect lightning, and they may seek a path to earth within the building, possibly resulting in a fire or electric shock. So what we're trying to do is, if we ground everything before it gets in, if we can get it to earth as quickly as possible. So at the panel, we're going to go ahead and this wire is broken here. The wire was meant to be attached to my ground rod or whatever this is, possibly a ground rod. And so if lightning were to hit those wires, we want to redirect them down to earth before it comes into the building. And that's kind of why we ground at the main panel. We always put a, like a ground rod or some type of grounding electrode at the panel. We also do it at every transformer on the poles, and we ground the system at the pole. So the utility automatically already does it. So if anything were to hit the power lines, we would want to direct them to earth and not into the building through some unwanted pathway. So that was so again, 240.250.4 is very critical to understand why we do what we do when it comes to grounding, okay? And we will use an equipment bonding to clear any ground faults. And what we're saying is we have to create effective ground fault pathways, and that's your job. That's the electrician's job, is to create anything in green in here. Those are effective ground fault pathways. And what we're saying is, if we ground the metal container and we take a wire and ground every outlet, we created a pathway back to the source, to all the way back to the source to the transformer. Okay, so there's an effective pathway all the way back to the transformer. And the main purpose, again, is to facilitate the operation of the breaker. So the breaker will trip underground faults. We want it to trip underground faults. Okay, so you can see here a wire has tripped against the frame. So the electrons are flowing on the red wire in this case from the transformer back this way. You can see the yellow pathway back, all the way back to the point that we ground, we've touched the panel or the enclosure. And now if everything's properly grounded, we would create a loop back to the system, back to the XO, which is in the transformer, allowing and facilitating this loop to now have a lot of current. So we bump up the current. We want it to be up high, enough to trip the breaker. So we have one breaker at the panel. We also have a main panel breaker. So we have two points that we might be able to trip in the system, and hopefully enough that it will protect the wires and won't damage the wires. So if everything's been designed properly, then my breaker protects the wires, and if that breaker trips, my wires will not melt down, causing further further damage to the building. So the idea is also that the wires can be reused. They're not like a fusible link. They're not meant to work one time only. Okay. Also notice that we have this green path, but we also have the ground rods here. We have a ground rod at the transformer. We have a ground rod at the main service. Some of the electrons do flow back through Earth from one rod to the other rod. Okay. Also, many studies have shown about 5% will flow back through that pathway. About 5% during these fault conditions. Okay, so in here, typically we'll have 5% of the current will flow down this way back to the source, but 95% will flow on the equipment ground. Okay, so that is the only thing you have to be aware of, is that rod to rod, sometimes for fault conditions, and if we wire this up incorrectly, by the way, if somebody did tie the neutral to the ground now, the equipment ground will be a current carrying conductor. And one day, if that happened and you happen to be working on these ground rods and under these fault conditions, you take it apart and you will see an arc, and hopefully you're not going to become part of that circuit, because that could kill you by not being so I just want to make you aware of this, that you literally could get killed by taking this wire off the ground rod without giving it much thought. Like this one here, like say you're going to change the main panel, or you start taking wires out because you're going to start you're going to change the main panel. If you have any electrical current flowing through this thing, you literally could get killed by removing this wire. So and that would be if somebody wired something improperly. They tied the neutral to it would not trip the breaker, but it would actually, it would cause current to flow on the equipment ground, okay? So what I typically do is when I get into my panels, I have a clamp-on meter, and I'll clamp it on the neutral and I'll clamp it on the ground, and I should see 0 amps on the ground. If I see anything on there, I've got something wrong. But also it could be induced current. So I'm expecting to see a little bit of current flowing, but not a large amount of current. So if I do have that happen, it's because I've got a problem in my electrical system. Somebody wired up. There's so many, the most ridiculous things, a lot of people out there, there's so many systems out there that have these dangerous conditions. And, but, they've been like that for a long time. And fortunately, nobody gets killed, but you know, until you come in there and find this. But if you're working on these, you need to be very aware of the fact that some of the current does flow to Earth. The dirt itself is not a good conductor. So the Earth is not a good conductor, so it would rather flow on the green wire back to the source than the Earth. But 5% of 100 amps is 5 amps, enough to kill you. Because remember, anything above 50 milliamps can actually hurt you, or 1/20th of an amp can actually cause the fibrillation of the heart, which means that your heart's not going to be pumping correctly, and it starts shutting down your system, you know, your blood flow to your brain. So we're not talking about that much current. That's why about 5 milliamps is how ground fault circuit interrupters, they start, they trip, because 10 milliamps can actually, you will actually sense your muscles, you'll sense tingling sensation, and things like that. Anyway, okay, like I told you, this grounding section is pretty involved, and it's actually a very important part. But I will tell you, going back to this one here, if you are working on a system, the best thing is to flip the main breaker. And if you want to be overly cautious, you can actually pull the meter. Pulling the meter off of there will cut all electricity. So let's say if you have that would be ultimately, you don't want that to happen. But if you pull the meter off the socket, it will cut out the power from the meter box all the way into the main, to the panels and all that stuff. So that's like an ultimate shut off. The only problem is the socket itself is energized, so you can't stick your fingers in any of that area. And so they have these plastic covers that fit on there in that case, if you ever have that condition. But and I've had to do that. I've had to do that before when I'm servicing. I found the main breaker actually was bad, so I had to change the main breaker. So the easiest thing was to pull out the meter socket so I could isolate the main breaker in that case. So just to make you aware of those things. If you shut the power off to the building, you shouldn't have any current flow on this the grounding electrical conductor. You shouldn't have any current on there. Okay. Okay, so in here, we're looking at the impedance of the equipment ground being 0.56 ohms is the resistance of this wire. In addition, we have the wire of the mains coming in where the power comes in to where the short occurred has a 0.05 amp. That added up to the 0.156 comes up with 0.206 ohms, which means that if we know the impedance of the circuit or the resistance of the circuit, that we can calculate the amount of current that we're going to have during a ground fault scenario. So in this case, we calculated that we should have 583 amps. 583 amps will trip this 100 amp breaker. So just so you know, we usually use, that's about a 500%, 500% of the amount of current of the breaker, and that's typically what we use for our calculations, is 500% of the breaker setting, as in the amount of current that we expect in our circuits. Okay, but our breaker will trip hopefully real quick. In this case, depending on what type of breaker we have. Here we have a 20 amp inverse time circuit breaker, and what it says is the higher the amperage, in this case we have 100 amps. So I'm looking at this point here and I'm looking at this point here. So we have a minimum and a maximum time, reaction time of the breaker. And Sorry about that. I had a phone call. So in here we have a maximum unlatching time for the breaker at 100 amps. Okay, so that's 100%, 500%, right? If it's a 20 amp breaker, the 20 amp breaker at 500% will unlatch between 5 to 20 seconds. Okay, right. So it's actually that's actually very slow time, by the way. Most of them will trip faster than that. But the idea with these inverse time breaker is that you give it enough time. So if it's a delayed reaction, is that what it's going to do? It's going to trip. Let me explain that here. The delayed action of the inverse time breaker sometimes is wanted because the amount of currents that we have maybe are just for real split seconds and they're not for long term. So anyway, just to sometimes we want that to take a little bit of time, but instantaneous breakers, on the other hand, anytime you would reach anything above 20 amps would trip pretty quick. And so instantaneous breakers kind of possibly create some problems because sometimes we do have those fluctuations of currents, like a motor, for example, that when you start the motor, you have an inrush, then it goes down to normal current, what we call full load current in the circuit. And then we can look at, in this case, 200% or 40 amp tripping would have a minimum unlatching time of 25 seconds to a maximum of 150 seconds for the breaker to trip. The wires possibly will get hot, but not enough that it will burn down the building during that time period. And so it's still, just something to think about. The higher the current, the quicker this thing will trip. The lower the current, the longer it's going to take for it to trip, between 25 and 150 seconds, right? Versus 5 seconds to 20 seconds for this 100 amp scenario, okay? So, these good charts that kind of show the clearance time for breakers, especially on an inverse time circuit breaker. And the numbers are actually a little bit high here. They're usually less than this. I don't, yeah, this is just an FYI, just so you're aware of this stuff, okay? Questions or comments, anybody? Okay. Bonding metal parts in buildings. So 250.4A4 says that we have to bond any any parts in a metal building, or any parts that are metal in a building, which means that if I have sprinkler pipe, I may have to ground it, or if I have a gas pipe, I may have to ground it. But that one's kind of a little bit iffy one, because some places with the gas piping, they don't want you, like in San Francisco, they don't want you to bond the gas pipe, but then most other places do want you to bond the gas pipe. Water pipe also will need to be bonded, and also any type of metal structure, metal buildings, metal I-beam. If you have a commercial industrial building, a lot of these are made out of metal beams, and so that all the beams have to be, well, we typically bond it at one point on the beam for the building, and then that'll be closest to where the main service is at, and that's where you would do it. So in this case, what we did is, let me go into here. So what we did is we took the steel, the structural steel, and we used it as a point to bring everything together. So we bonded our electrical system to the building steel, and if the building steel is going to earth properly, because sometimes building steels will actually float. So what they do is they'll actually have it float, like for earthquakes and seismic activity. They literally have buildings that literally float, and so the building is not solidly attached to the earth, to the concrete, the concrete footings and all that stuff. So sometimes these will sit on rollers, which I always thought was kind of an interesting concept of having these buildings kind of floating because of earthquakes, and to allow that flexibility of the building to move during an earthquake instead of being rigidly, and shaken to a point that it might fall apart. Hence why we see like any solid structures don't do as well. Like for example, concrete buildings. That's why we don't do that many concrete buildings here in California. From the standpoint that we'll like in other countries, we'll build the whole house. It'll be all concrete. The second floor. I mean, everything will be all concrete. The roof will be concrete. And in California, we found that wooden structures have that flexibility. Hence, we like to do wooden structures for houses. They seem to do better during earthquakes than have something that's a concrete. I always thought a concrete building is like, I would rather have a house that's all concrete, but it doesn't work too well during an earthquake. Anyway, so most of these buildings, what I was talking about is the structural steel. If it's bolted into the ground, it's a solidly bolted type system. So the ones that I'm talking about that are floating are like buildings in downtown San Francisco, downtown Oakland even has some, where literally the building, LA, you'll see these buildings that are not solidly grounded, attached to the earth or to the ground. So the beams have to be, you have to put a little bit more thought. Usually you put a jumper from one side of the beam down to earth. So there's ways to ground it. And as long as your beams are properly grounded, you can use that as a pathway to bond everything. So here we went from the building steel to the water pipe. We can actually go from the building steel to the sprinkler pipe, and so on, okay? And then that can be tied into the electrical system right through that main bonding jumper right here, and that ties into the ground and the neutral eventually, okay? Questions? Nobody? Okay. And the other one's effective ground fault current path. We talked about that. It was making sure you have making sure you have an effective ground path of that's a low impedance. So this is actually a really important point. Metal parts of electrical equipment must be bonded to the supply source in a manner that creates a low impedance path for ground fault current to open the circuit over current device. So if we create a low impedance pathway, then that means low resistance, low inductive and capacitive reactance in the circuit. Then we actually create a low impedance pathway, which can facilitate the operation of the breaker. And I've said that before, is that the main purpose of a ground pathway is to actually facilitate the operation of the breaker. So that's a kind of another effect, another thing that we have to make sure we ensure is that everything is grounded properly and that it is a good ground pathway back to the source, okay? Circuit conductors that are grouped together need to go into the same conduit. So this is a violation by running the ground on the outside. You can't do that. When we're installing all conductors in the circuit, the same raceway, trench, cord, whatever cable, tray, we minimize induction heat in metallic raceways and enclosures and help maintain a low impedance fault current pathway. And so those would need to be inside the conduit in this case. And then because the earth isn't suitable to serve as a required effective ground path, we still have to run a ground in our conduits. Now, sometimes we will do these ground rods by these poles. Some places that have more lightning activity will require us to actually either do a ground rod, or what I've done also, like, you go out to Fairfield, and all the poles, parking lot lights have to have this wire going down to the bottom of the concrete base. And you before you pour the concrete, you got to wrap this wire at the very bottom. and have the wire come in and land, like in here, land inside the that's called a manhole or a hen hole. So the hand hole, you have you land the ground in there, okay? Or you may have to run a ground rod if you didn't do it properly. So that would be you're usually trying to avoid this type of running a ground rod. Okay, and the purpose of the ground rod is if the lightning were to hit the pole, that the lightning would actually be diverted to earth through this pole and not into the electrical system through the equipment ground. That's the whole main purpose of doing it this way. Okay, so if you've done metal fences before, they also do that for metal fences, around large metal fences that go around permanent ones. You know, a lot of the, you know, facilities like, you know, high security areas will do metal fencing. You have to run those ground rods also. So for lightning purposes, you ground it and have a place for it to travel down to earth instead of down the fence and possibly hurt somebody. But earth itself is not a good pathway. So I already told you that, because resistance can be upwards of 25 ohms to ground, and you can just do the math. 4.8 amps may not be enough to trip the 20 amp breaker. In this case, we just did Ohm's law, resistance of 25 ohms. Sacramento Valley, I know I've done a lot of testing on the ground. I found that, you know, you can find 10 ohms, 8 ohms, and also it changes with the seasons. So for example, in summertime, you might find 12 ohms. In the wintertime, you might find 8 ohms. So it changes, but still, if you do the math on it, 8 ohms still is not enough to trip a 20 amp breaker, you know, so 8 ohms would put it at 15 amps, and 15 amps would still not trip a 20 amp breaker. So earth itself is not an area, we cannot be dependent on earth as a way to ground our stuff, right? It does not work. And actually, this is the situation where that little girl got, well, not exactly like this one, but because the neutral was run to the light pole. Here you're not showing the neutral. But the thing is, this is just to show you that if we use the earth to get, instead of the neutral or the ground, it's not a good pathway. But that little girl that got killed in that Freeport car wash, this is basically, in a sense, what happened is that they didn't run a ground wire, and so something shorted out, went or ground faulted, and so they were using the earth as a return path. So they didn't pull the ground properly or install the ground properly, and that's why the breaker never tripped. And then she became the path of this current because she had less resistance in her body, you know, especially being small. She was like 7 years old, so the current went through her and ended up killing her. Not enough to trip the breaker again, you know. So we have to be really careful about knowing how to ground things properly. So under ground fault scenarios, we do trip the breaker. We don't want it okay. Earth is not in effect the ground path. Now, this is actually more of the scenario what I was talking about, that little girl getting killed. They did bring a hot and a neutral in here, but they just did not ground the system properly. And so they're showing a ground rod in here, but they didn't put any equipment ground in the PVC pipe. So this is exactly, in essence, what happened with that little girl. And any electrician should know how you know, kind of know why we ground and how we ground, and, you know, what we avoid. And this is a situation we're trying to avoid by properly grounding things. Okay. And the other thing about this effect, which actually this is kind of interesting, because if you put a ground rod into the earth, how does the dissipation of the electrons occur is somewhat like in this method, and also voltage drops according to the further you are from the ground rod. The voltage will drop. The thing about it is, there's a couple things that are in vogue in here. Is first, I always think of how, you know, going back to Benjamin Franklin and his he thought that voltage actually dissipated straight into the earth, and he never thought of it being this way. It's one of his, one of his theories that was disproved later on. How the dissipation of the voltage occurs and the currents and the electrons flowing through here. He thought it went into the center of the earth or straight down, so that's not what happens. We have, so once it hits the ground rod, it will start traveling horizontally and kind of in this pattern here. And there will be voltage drops that occur throughout the system. So anyway, we'll leave it at that. And yeah, this is that scenario with the little girl having the two circuit, no ground in here, and how Earth itself will have voltage dropping through here. And so, you will have a certain amount of voltage. In this case, he's in the second ring here, where you have second ring is 3 foot away. Well, actually, but it says 75%. So you have about a 90 volt drop here. So from the pole out to the outer edge where he's got his knee, it's supposed to be 3 feet distance. There's 90 volts of voltage drop that's occurring on the body. And that is enough to have current flow, and the current flow will occur through that person depending on how much resistance they have. Also, obviously, in the little girl's scenario, she was, had a smaller body, had less resistance, causing more current to flow through her body, not allowing her to get away. And I'll tell you, I've been in these situations where I've done exactly this, but I don't put my knee on the ground. The problem is, one time I was at Cal Expo, and I was working on 277 volt lights, and I happened to have just touched the wires by accident. But I was thinking, okay, I'm standing on my boots, and I'm thinking, okay, my boots offer some type of insulation. No, I felt it, and what happened is in my boot, I had a little screw on the bottom of my boot, and so the boot itself was I was not isolated or insulated. I was actually still conductive through that screw that was in all the way almost to the bottom of my foot, and because of the moisture and everything else, it actually became conductive. So don't make assumptions that your boots actually protect you against these type of situations, because they will not. Anyway, just keep that in mind. In this case, he's got his knee on there, so obviously he doesn't have any insulation. So, and we're still kind of defining things. This one, what is an ungrounded system? And you can see here, this system is not connected to Earth. We still ground all our boxes and everything else, but if there was a hot that did touch the frame, nothing would happen. It would have nowhere to go, because there's no way for the source, like the ground, the equipment ground, to get the current to flow back into the system. So we would not have any current flow at this point. Nothing would happen. This is kind of why the Europeans like their ungrounded systems, because it's safer. But that's only if we did have a fault detector. If we had something that actually told me that something went to ground, that then that would be the only way you would know if something went to Earth or to the equipment ground, if something did land. Because if you go grab, let's say, a second wire, if you do touch another wire in the system, now you've completed the path. If you are standing on something that's energized, you are going to have stuff go back into the system, but you're becoming that path instead of the ground, the bonding jumper between the equipment ground and the system. It's called the main bonding jumper, or the system bonding jumper, SBJ. Then you're becoming the system bonding jumper. Okay, so. This has always been controversial, as in, is it safer, is it not? And so people have kind of tossed this back and forth. And there's, one of our issues. So, for example, the United States likes to do grounded systems because we don't have any, we have quite a bit of resources, especially with copper in the United States. We're one of the #1 producers of copper in the world, which means that the Europeans don't have access to these unlimited resources. They are very limited, hence one of the main reasons for their colonization of other countries or other parts of the world was because they were trying to get resources, back into Europe, and there's always been a limited, limited resource by nature, by the way it's the way it eventually evolved through time. That there's limited resources, like limited copper, limited energy. They don't have much for oil, not much for. They don't have much in gas and so on. So they're dependent on like the Russians for gas, or Ukrainians, and in other countries to give them their energy sources and stuff like that. The point of it is that they've chosen to take on these systems the way they do it because of the limitation of the resources. And actually some of this does stem from World War II, why they went to the ungrounded system, because of the limitation of copper during World War II, where they needed to make and use it for brass in order to make bullets and projectiles and so on like that. So some of it is economic, why they did certain things. Okay, it doesn't mean it's better or.
So
Okay, what's that?
Is it a pretty common practice to amp clamp your ground when you show up to like an unknown problem?
So to clamp to what are you talking about? Help me out. Let me better understand.
So like you say you showed up to an ungrounded system, you knew it was ungrounded, something was wrong with it. Would it be like pretty standard for you to walk up and be one of the first things to your ground?
So yeah, so either it was designed for it to be grounded or it's designed not to be grounded. And so if it was designed to be ungrounded, then we leave it as it was. Okay.
Yeah, no, I mean from like a safety standpoint, would you want to check to make sure that you weren't out on your ground?
So just to make sure, a lot of times we ground wires while we're working on them. So we'll intentionally like clamp our hot wires. This would be if it's off, right? We do this, like linemen will do this with the power lines. Anytime they're working on, they clamp all their wires and take it to earth. So if anything did energize, from far away, whatever, that, and you're working on pipelines that have the sources are very far away. And so if you are working on this stuff, it would be of common practice to actually ground your system while you're working on it. In other words, you don't want to be the path, you want to ground it to earth for safety reasons. So we have actual special equipment that will ground all the wires with. You clamp it on there, and then you put it on the ground rod and then tie it to earth. But it's only while we're working on the system. So that's especially on those longer, the ones that we don't, where we don't see the breakers, stuff like that. We're talking about miles in distance, stuff like that. Linemen always do it on their power lines. But I don't know if that's what you're asking on that one.
Yeah, kind of. We did something similar on the pipelines. Yeah, we had to. So, like along the pipeline, before you even touch any wire that's attached to it, you got to take an AC reading to make sure that it's not getting induced from the power lines or anything.
Yeah. And then what do you do with the wires? Do you ground them at that point if you're going to work on them?
We can't. We only check for AC, and if AC is above 15 volts, then we would stop work.
Oh, okay.
And at that point, somebody would come in and they put in like a positive, they call it a positive cell replacement, because we have DC intentionally going to pipeline and we need to remove the AC. So they filter out the AC and allow ground.
Yep. Yeah. And that's because of the length of those wires, and it does induce, you get the long, especially in the proximity, you induce into it a lot easier. So especially on those lower voltage systems, it's pretty common. But it's the distances that you're dealing with is why that's happening. So. Okay, I'm going to stop right now. I'm going to have to continue. Let me see here.